Hello, everyone. I am Mitsunori Waimura of Ritsumeikan University. Let's start the 5th week of the Advanced Topics in Robot Control. This week begins with a continuation of adaptive control we discussed last week. Therefore, we first prove the stability of the robot motion when we use the basic adaptive control. Next, I would like to introduce adaptive control for multi-joint robots. Finally, we prove the stability of the robot motion when we use adaptive control for a multi-joint robot. Last week, I introduced an adaptive law to estimate parameters. However, I did not explain the principle of why this equation can estimate parameters. It is very difficult to clearly explain that principle. In fact, there are few textbooks or literature that explain why this equation can estimate the parameters, and only a few researchers have a deep understanding of the reasons. On the other hand, we can mathematically prove the stability of the control system. One explanation for why this adaptive law works properly is that we can prove the stability of the control system. Therefore, let's consider the stability of the control system when we use the basic adaptive control. First, as in the stability analysis of the computed torque method, the Lyapunov function v should include terms for the squares of the velocity error and angular error. For these error terms, we set the coefficients of 1/2 I bar and 1/2 kp. Therefore, we can prove that the error of the joint angular velocity and angle decreases if the Lyapunov function v decreases. Next, let's add the term of the squared error of the actual and estimated parameters. In this term, we set the coefficient to be 1 divided by the 2 gamma. Therefore, we can also prove that as the Lyapunov function v decreases, the error of the estimated parameters also decreases. All of these terms are the square of the variable multiplied by a positive coefficient. Therefore, the Lyapunov function v, which is the sum of them, is always positive. Now let's differentiate v with respect to time t to see if the Lyapunov function v decreases. The differentiation of the first two terms is the same as for the computed torque method. The derivative in the third term is like this equation, because the I bar is a constant and disappears when it is differentiated by time. We then substitute the motion equation with adaptive control into I bar q2 dot of the first parentheses, and obtain this equation. The only difference from the case of the computed torque method is the I bar hat in the first parenthesis. Therefore, the term relating to the third term in the first parenthesis cancels out the second term of the overall right-side equation. The term relating to fourth term in the first parenthesis is negative. Furthermore, the first and second terms in the first parenthesis can be factored by QD2 dot, since they both contain QD2 dot. By reflecting them in the equation, we get this equation. In the case of the computed torque method, since we did not have the first and third terms and the second term was negative, we could make V dot negative. So let's consider whether we can cancel the first and third terms out. The designer of the controller can design this I bar hat dot freely. Since the first and third terms both contain I bar minus I bar hat, let I bar hat dot be gamma QD2 dot QD dot minus Q dot, and these terms cancel each other out. Therefore, we can guarantee the stability of the control system if we use the adaptive law as described so far. Note, however, that this analysis does not directly mean that the estimated parameter I bar hat converges to the actual parameter I bar. In a simple system such as this one, the estimated parameters actually converge to the actual parameters, but this may not be the case in a complex system. Even so, there is no problem in achieving the control objective of CP control, since the convergence of the motion is directly guaranteed. The above is one explanation of why the adaptive law is such an equation. I think, however, it's hard to understand the principle of the adaptive law because the above is just a mathematical explanation. If you want to understand the deeper principle, figure it out for yourself. Next, I would like to show how to apply adaptive control to a multi-joint robot. The control objective of adaptive control is, as is the case with the computed torque method, to converge the joint angle vector and joint angular velocity vector to the desired ones that varies with time. The application of adaptive control to multi-joint robots was proposed by J. Slotine and W. Lee in 1987. Adaptive control is originally proposed for a linear system. Therefore, since the motion equation of the robot is nonlinear, the stability cannot be guaranteed if we apply the original adaptive control to a multi-joint robot. In the adaptive control proposed by J. Slotine and W. Lee, The stability of the adaptive control can be guaranteed even if the robot dynamics are nonlinear by exploiting the characteristics of the robot dynamics. So, let me first introduce one of the characteristics of robot dynamics. One of the characteristics is that the centrifugal Coriolis term H can be expressed as the product of the matrix H and the joint angular velocity vector q dot. The matrix H depends on the joint angle vector q and the joint angular velocity vector q dot. When you create a simulation and actually calculate the centrifugal Coriolis term, you know each element of the centrifugal Coriolis term is always multiplied by two variables of angular joint velocity. Therefore we express the centrifugal Coriolis term as the product of the matrix H and the joint angular velocity vector q dot. Another characteristic of the robot dynamics is that the robot dynamics can be expressed as the product of the matrix Y and a parameter vector theta as in this equation, where this matrix Y is a matrix that depends on the joint angle, angular velocity, and angular acceleration, but does not depend on the parameters of the robot. The parameter vector theta is, conversely, a vector that depends only on the constant parameters of the robot and does not depend on the joint angle, angular velocity or angular acceleration. In the simplest example, I bar is the corresponding part to the parameter vector theta and q2 dot is the corresponding part to the matrix Y. The motion equation of the robot is complex, but the physical parameters of the robot, such as weight and link length, always appear in the form of multiplication with variables. You can actually confirm this characteristic by using the example of a two-joint robot to see for yourself. Note that the matrix Y is defined as a function with respect to two joint angular velocity vectors q dot. The first q dot is the q dot of the contents of the matrix H. The second q dot is the q dot that appears in the form of the multiplication with the matrix H. The matrix Y is independent of the robot parameters, so we can compute the matrix Y even if we don't know the robot parameters. Using the above characteristics, we compute an estimate of the torque required to generate the desired motion, theta hat. By using the vector of the estimated robot parameters theta hat, then tau d hat is theta hat multiplied by y. However, the second velocity vector q dot in the matrix Y has been replaced by qr dot. This qr dot is the desired angular velocity vector qd dot plus the joint angle error qd minus q multiplied by a positive constant alpha. The Q2 dot in the matrix Y are also replaced by QR2 dot. Because we use such a vector QR, adaptive control is slightly more complicated than in the case of the computed torque method, but the principle for calculating the required torque is the same. The reason why we introduce this difference is that we need to use it in the stability analysis. The adaptation law for the parameter vector theta hat is designed like this, where the gamma is an adaptive gain matrix that the designer of the controller is free to set within the range of the positive definite matrix. When the matrix Y is used for an adaptive law in this way, the matrix Y is called a regressor. QR dot minus Q dot is defined as Z for the future analysis. Thus, although the adaptive law is more complex than the simplest case, the structure itself is the same. Therefore, if you understand the adaptive law for the simplest well, the multi-joint robot case will also be easier to understand. The reason for designing such an adaptive law is explained in the stability analysis. The controller is designed like this. The term tau hat is an estimate of the torque required to generate the desired motion. Therefore, if tau hat is the torque required to generate the desired motion tau, then this term realizes the tracking of the joint angle acceleration. By considering the definition of QR.NZ, we can see that the vector z in the second right-hand side term is the sum of the error of the joint angular velocity and joint angle. Therefore, the term of kpz plays the role of the error feedback feeding of the joint angular velocity and joint angle. Kp is a feedback gain matrix that the designer of the controller freely set within the range of a positive definite matrix. Let's implement adaptive control for a multi-joint robot in a MATLAB simulation so that you can use adaptive control. To create this simulation easier, let's reuse the simulation of the computed torque method applied to the two-joint robot. For the simulation, let's first obtain the motion equation of the two-joint robot separated by a regressor matrix Y and a parameter vector theta. Once that is done, let's define the estimated parameter vector theta hat as the input to the controller block and calculate the obtained regressor matrix Y in the controller block. Once you calculate the matrix Y, the actuator torque vector tau can easily be calculated from the equation of the controller and the tau hat. Next, let's define the adaptive gain matrix gamma and compute the time derivative of the parameter vector theta hat using the equation of the adaptive law. The time derivative of the parameter vector theta hat should be output from the controller block and integrated using a integrator block. Let's input the output of that integrator block to the controller block as the parameter vector theta hat. Other parts are the same as that of the computed torque method simulation. To check the convergence of the parameters, let's display the actual and estimated parameters on a single graph. You don't have to show all the parameters, but you should show one or more of them. As always, check to see if the robot joint angle converged to the desired angle. This exercise is, as always, this week's homework assignment. So let's take a moment and create a simulation program. Now, let's analyze the stability of the control system when adaptive control is applied to a multi-joint robot. First of all, the Lyapunov function V is defined in this way. The first term on the right-hand side represents the magnitude of the control error since the inertia matrix M is a positive definite matrix and Z is the sum of the joint angle and the joint angular velocity errors. The second term on the right-hand side is the quadratic form of the error between the parameter estimate vector theta hat and the actual parameter vector theta, which represents the magnitude of the parameter estimate error since the adaptive gain matrix gamma is a positive definite matrix. Due to the nature of positive definite matrices, if the gamma is a positive definite matrix, then its inverse is also a positive definite matrix. Since both of these terms have positive values, the Lyapunov function V is always greater than or equal to 0. Therefore, as the Lyapunov function V decreases, the control and parameter estimation errors decrease. So, let's differentiate the Lyapunov function V by time. Applying the previous analyses, the time derivative of V can be obtained in this way. Next, we transform the mz dot using the motion equation with adaptive control. Mz dot can be rewritten by this equation from the definition of Z. Substitute the robot dynamics with adaptive control into the MQ2 dot in this equation. The robot dynamics with adaptive control is obtained by substituting the control law of adaptive control for the right side of the motion equation of the robot, which gives this equation. By substituting this equation into the mz dot of the equation of V dot, then we obtain this equation. Note that we also substituted the adaptive law into the theta hat dot. Next, we add the terms HQR dot in the first parenthesis. Note that these terms do not change the equation content, since the sum of them is equivalent to the zero vector. Since the first and second terms on the whole right side equation are the ones where the transposition of Z is multiplied from the left, we put the second term in the first term. Here, the second and third terms in the first parenthesis are Hz from the definition of vector Z. The first, fourth and sixth terms are Y theta from the definition of the regressor used for the adaptation law. Taking them into account, the previous equation can be summarized as follows. However, we substituted Y theta hat for Todd hat and transposed the entire second term on the right-hand side. Here, by using the property of the characteristic of the robot dynamics that H half m dot is the skew-symmetric matrix. The term of the second term in the first parenthesis is 0. A skew-symmetric matrix is a matrix whose quadratic form is 0. We also use this characteristic when analyzing the stability of the passivity-based control. The first and third terms in the first parenthesis are multiplied by y theta minus theta hat. The term relating to this term is cancelled out by the second term of the overall equation. Therefore, the only remaining term is the term of the fourth term in the first parenthesis. Therefore, V dot will eventually be this equation. Since Kp is a positive definite matrix, V dot will be negative. Therefore, it is shown that V decreases monotonically with time, proving the stability of the control system. Note, however, that the estimated parameter vector theta has not been proven to converge to the actual parameter vector theta. Nevertheless, the convergence of the motion is guaranteed, so the control objective is achieved. In conclusion, it has been proven that adaptive control can achieve CP control without knowing the robot parameters in advance. The passivity-based and adaptive control methods that have been introduced so far are excellent control methods that realize control objectives without using the detailed information of a robot, even though the robot has nonlinear dynamics. Conventional nonlinear control theory has not provided such a control method. The reason for this seems to be that nonlinear control theory has dealt with general systems. In contrast, these robot control methods solve problems by exploiting the unique structure of robot dynamics. For example, passivity-based control takes advantage of the energy conservation law, which is a physical property of robots. Adaptive control takes advantage of the characteristics of the centrifugal Coriolis term and the fact that a part of the dynamics is represented by a skew-symmetric matrix. By exploiting these characteristics, we can solve problems that cannot be solved by general nonlinear control theory. These are unique and important advantages of robot control that even influence other control theories, such as nonlinear control theory. Finally, I would like to introduce homework for this week. This week's homework is to create the MATLAB simulation I described this week and submit it as a report. In the report, please include the figure of the simulation model of Simulink, the program source of the robot dynamics block, the program source of the controller block, the simulation result graph, and the explanation of the simulation contents and the simulation result. Please submit the created report through Manabar. That concludes this week's class. Thank you for your hard work.